Okay, so what is the latest class that we've talked about? Okay, so when we are referring to cephalopods, who are we talking about? Squids is one. Okay. And the third one? Yes. It's a nautilus, but I always just give the plural form of nautiloids. So octopods, and then squids is its own plural, if that makes any sense, right? See, there's another word that had came to my mind with an animal, just like deer is one. I can't think of another animal that's its own plural. Sheep, okay, that's not what I had come up with, but you're not wrong, okay? And no, I don't sit up all night trying to think, what's the animal that is singular and plural at the same time? But so those are correct. Now, one of the things that we want to stand out in your mind, okay, when it comes to looking at the cuttlefish from the very brief, well, we'll come back to that because that's an unfair question. So who are some other mollusks that we've talked about? Okay, clams and, okay, and then what are our classes for that? Okay, so then, the feeding with the animals, who would have the most complex sensory organs, do you think? Which class? You sure? Are you sure? Okay, so the cephalopods, I mean, just look at what we've seen with the cuttlefish so far. That takes a high range of intelligence to do that, just because of what it can do for camouflage. And it's one of the subtle things that sometimes we try to explain why animals may have developed or changed different aspects with them. What did one of the professors or researchers say that this is what I believe why cephalopods, especially cuttlefish, why did they lose their shell, went from the outside to go to the inside? And that's exactly what it did. But when you lose, so a shell is a unifying characteristic, so it's going to be a protective function. If that's what we were to say, who would be the most protected of all of our mollusks? If we just look at the shell as the most important aspect of protection. Say that again. Clams. You had said. Okay. Because I just wanted to be sure, because I thought I heard fish, and then but you meant cuttlefish, and then say that doesn't quite sound. That's why I wanted to clarify. I swear to God, I'm listening. Okay. So, but with that. So we could say that clams have the most protection because their shell is on the outside. So why would the cuttlefish then have a design to lose that shell on the outside and move it inside? So if it has the ability to camouflage, that's a very distinct advantage to hide them from who? From more active predators, because if they can't find you, they can't eat you. So what would have to happen is they had to lose or have the ability to camouflage to hide themselves from predators. That's right. Okay. So again, one of the things that you have to know what you're looking for when we see this. When the cuttlefish or squid or octopod is moving, not so much with that of the nautiloids, because their shell is still on the outside, okay? So even when these are moving, they're either going with the water current, just bobbing along, Or how do they move in a specific direction? What did we say yesterday? What's actually happening with that structure? Because what the example we gave was if we wanted to move liquids from here, it's such a bright background, from here into here, okay, how would we do that with trying to ensure not to spill? You'd use a funnel. So where is the speed, okay? Where's the speed the fastest? At the top of the funnel or at the bottom? Yeah, it's going to be at the bottom. That's actually a mathematical principle. That's Pascal's principle, and that's, so you could say we're copying what nature does. So if it's faster at the bottom, which it is, when that mantle cavity contracts, it's going to push water through at a higher rate, and when it does that, it's going to push it in the opposite direction. Okay, so our first class then, or excuse me, our first animal of this class then would be your nautiloids. I don't know if I'm going to get that paper to you today. It's looking like not, but we'll worry about that later on. So we're always going to make a comparison with animals within the phylum. They're in different classes, but we might make comparisons. In this case, we're going to make a comparison with animals within the same class. We did that with sponges, okay? And then we compared all three classes of cnidarians, okay? One is sessile its whole life, one is sessile and becomes free swimming, and another one is born free swimming. In this case, for some reason, and I really don't have an answer for this, if the metabolism of these animals, which I would think is really, really slow, why would they need two pairs of gills? Okay? That is really an answer I really don't have, but nonetheless, for some reason, nature had selected them to have two pairs of gills. The only thing that I can think of is it has to deal with their locomotion. Because if they're going to move with their gas chambers, they have to get that oxygen out of the water somehow, or air out of the water. And maybe it's just made more efficiently with two gills. Because, okay, just have these one pair of gills, where these have two pairs. And of course, looking at the number of appendages they have, if you were to see a little later on when we get to the vertebrates, we not only just experiment with sharks or dissect them. Before we do that, there's a video, it's called the Virtuarium, where they go back in time and virtually look at some of these sharks. And you'll see examples of nautiloids, and you're going to see a lot of these tentacles, but some of them are actually quite small. So even though you can't see them, they are certainly there. All right. And then, according to our schedule, tomorrow's activity, which we will still have scheduled for tomorrow, this is something that you'll be able to see, okay? And of course, this is why these animals get their names, because they have the 8 arms. With squids, you'll actually see they'll have these 8 appendages, plus 2 more that are actually a little longer than that of the rest of them. And then that's why we would say, okay, they've got 10 appendages, these 8 arms, with then, of course, 2 retracting tentacles. Now, from prior knowledge, what would that mean to you then? when you see that term tentacles. You're going to hit yourself over the head and say, I knew that. From prior knowledge, what would we refer to animals with tentacles? We might have said it, but I'm back here. Yes, and what's significant about jellyfish? What do they produce? Venom, that's right. So I believe we look at these, the author says poisonous. I really don't like that term because I think when it comes to a type of venom, it comes from these type of structures. Okay, so venom is different than that of poison. And I think that's a better way of looking at that. Let's see here. Where does that put us? Where's octopods? Okay, I just want to get down to here, okay, to these color changes, okay. So to me, possibly, not only are these animals getting more oxygen, especially the nautiloids, but they're going to probably receive even more just because they've got two pairs of gills. And that could be a reason that they need two pairs, is because maybe it's such an idea that the movement of the water through the mantle cavity is more efficient for grabbing oxygen, where that's not the case with nautiloids because they're just too slow. So one of the things I haven't quite figured out yet as well, when we look at those cuttlefish, aren't, and I don't know how many times I've been told this, probably 90 times, I don't know. That number just popped in my head because of the number of appendages on a nautiloid. But your primary colors, aren't they red, blue, and green? Or is yellow a primary color? Green is not a primary color. Okay, so you said red, yellow, and okay. So in the skin of these cuttlefish, that's what was in the cuttlefish. I think that sounds right. And then for some reason, when those skin muscles, they start to open, in the epidermis, I would say, because then on the dermal layer, they have different types of colors. Blue, reds. Okay. So I don't see how they can do bioluminescence, if you had seen that from the video yesterday, which is actually pretty astounding. So that's why we'd have to say these animals certainly have a very complex, per se, nervous system that takes complex thought to do that. Okay, so we will stop there for today. We'll continue with the cuttlefish because I think we're able to put this on the Science Channel because I believe even though it's copyrighted, public broadcasting allows us to do that because they're the owner of this. So we will continue with that. And just let me get this set. It's getting warm in here, isn't it? Or am I imagining things? Okay, so this will be obviously right where we left off.
burn bright and die young. Some live slightly longer and die, but all of them don't live very long. So it's probably only 18 months to 2 years old is how long they live.
With such a short lifespan, it's even more surprising how smart these creatures seem to be. Intelligence is all about learning to adapt to new situations. Here at Millersville University in Pennsylvania, Gene Bowl wants to figure out just how much and how fast cuttlefish can learn.
I think cuttlefish are remarkably intelligent animals. So the issue is, am I smart enough to find out how smart they are?
For nearly 20 years, Gene has been running tests with cuttlefish and their more famous cousin, the octopus.
I began with octopuses because there are no cuttlefish in the Americas, so like most Americans, I'd never heard of them. Octopuses love to destroy lab equipment. If they can possibly rip something apart, they will. And in terms of their performance in experiments, octopuses are unbelievably erratic. One day they'll be brilliant, and the next 5 days they'll act like they don't know anything at all.
Hey everybody, how are you today?
Once I got started working with cuttlefish, they're very practical animals to work with. They're very easy and they're very engaging. And then on top of that, it looks like their brain size relative to body size is perhaps even larger than octopuses. And it would be really wonderful if we could just figure out what they're doing with all that brain.
To test her cuttlefish, Gene has created a special enclosure fashioned from a plastic trash barrel, which the animals must try to escape from.
The real difficulty for me is to find out how to ask them so that they can tell me what they know. They're certainly not going to tell me verbally. So I have to design a clever enough experiment that their behavior can tell me what they know. And that's what's really challenging and really, in many ways, exciting.
13 research subjects with names like Bubbles, Goofy, and Crook are tested 3 times a day over several months.
Who have we got? We got Crook. Okay, what time is it?
Their job is to negotiate a simple maze and to find their way out as quickly as possible.
The cuttlefish maze has a starting tube where they go in and just calm down for a few seconds.
In she goes, she's in.
3, 2, 1.
Doors open.
And then there's a larger arena, and they have to decide whether to go to right or left. And there are features in there to help them distinguish that.
In each trial, only one of the 2 exit doors is open. The cuttlefish has to look for clues to pick the right one. If there's a piece of plastic seaweed in the enclosure, then the striped door will lead to freedom. But if the cuttlefish enters the maze and sees a big brick instead, then the solid door is the way to go. If the cuttlefish picks the wrong door, she'll be blocked by clear plastic.
All right, this is 10.
So can a cuttlefish learn these rules?
In you go.
The current problem that I'm working on is conditional discrimination learning. Can you remember the 2 things at once?
1.
Open. She's in.
Okay, starting.
And we have good evidence that the cuttlefish can do this, which is truly extraordinary for an invertebrate animal.
There she goes. She is out.
Break time.
The cuttlefish are able to recognize and remember at least 2 rules or conditions for finding the open exit. That's a level of intelligence much more common among creatures that possess a backbone.
So what's really exciting about cuttlefish intelligence is we know that their relatives are clams and snails. Those are not animals that have a need for great intelligence. So whatever happened to cuttlefish was different.
I think one of the reasons they have to be so smart is they've given up their external body armor like a snail has. They're soft, they're vulnerable, they can be eaten. Everything in the ocean eats a cuttlefish. So these animals have to get by their wits, so to speak. They have to be smart. I think it's safe to say that cuttlefish are definitely as smart as fish. And in fact, they're as smart as maybe even some animals like birds and mammals and other things we consider to be smarter animals.
The cuttlefish's big brain, together with its amazing camouflage, probably evolved so they could survive in dangerous environments filled with hungry fishes. But one cuttlefish might have acquired another secret weapon. Back in the tropics, Mark Norman and Ronald Cerrante are searching for Mark's favorite cuttlefish, who's managed to thrive in a unique and threatening landscape.
These muck dives on sand and mud areas are very different. They feel very solemn and dark and moody. You have these black plains going everywhere. The few animals you do pass are either covered in poisonous spines or pretending to be dead leaves. You get this feeling that it's just oppressed by predators.
This is a place of the weird and the wonderful, where standing out or blending in all depends on whether you are predator or prey. It's one of the few places you'll find the rare mimic octopus. But the strangest of them all is a creature called the flamboyant cuttlefish. For a start, it's walking, not swimming.
It's still really foreign for me to watch a cuttlefish walking around on the seafloor. They'd actually look like these prehistoric lumbering monsters sort of walking through these ancient black deserts.
This enigmatic animal has made a huge impression on Mark, despite the fact it's only a couple of inches long. Although the flamboyant cuttlefish walks most of the time, it can swim, but just barely. What's wrong? Cuttlefish get their name from their cuttle bone, a chalky internal shell filled with gas that allows them to float. But the tiny flamboyant cuttlebone has shrunk so much, it can't float for very long.
They seem to have a really gentle nature. They flap up into the water, they settle down again, and they go back to walking along the seafloor, back into camouflage, back into feeding almost straight away, looking for something to eat out on the mud.
Like its big brothers, this cuttlefish has to grow fast and is often on the hunt. But to catch a tiny glass shrimp takes very good eyesight and patience. Stalking its meal in spiky disguise, it aims its feeding tentacles like a pool player, ready to hit the target. Eat and be eaten. For every creature, there's a hunter lurking. These open plains don't offer much cover, and to be out and about in broad daylight is risky, especially if you're neither fast nor big. Predators are a constant threat, and this is when the flamboyant cuttlefish earns its name. Whenever it feels threatened, it puts on an alarming display.
When something comes too close, they'll flare up the arms and they walk around flashing these colours and advertising these really bright colour patterns. And I think this is advertising the fact that they're poisonous to eat. If anybody gets too close, even like a diver, they show all the bright colours and it says, back off, I'm poisonous. It's either pretending it's deadly as hell and trying to mimic something else that's dangerous, or it's walking around confident that it itself is deadly.
Clearly, the flamboyant stands out from the rest of the cuttle pack. But is it just a big bluff, or the real thing? Is it poisonous or not? To find out, Mark and Ronald need to look for a full-grown animal, and freshly laid eggs are a good sign that a mature female has passed through recently. Hidden under coconut shells, they find some flamboyant eggs. The mother should be nearby. In this bleak landscape, it's a challenge for a flamboyant mother to find a safe spot for her eggs. Without rocks or caves, old shells are the next best thing. Compared to the egg-laying frenzy of her giant cousins, hers is a quiet affair. She lays up to 100 eggs, a truly exhausting task. And with the laying done, she'll soon die naturally. But there's one more important mission she can help with: assisting Mark with his toxin studies.
If this animal does turn out to be deadly, to be toxic, it will be the first cuttlefish in the world that's known to be poisonous. We could be seeing a whole change in the evolution of these animals. I'm really fascinated on what it is about them that's poisonous. Do they have a poisonous bite? Is all their flesh poisonous? Can they squirt poisonous ink?
Mark will have to take her back to the venom labs in Australia to unravel her potentially deadly secret. The winter storms have finally passed, and the deserted mating grounds of the Australian giant cuttlefish slowly begin to warm. The parents died more than 3 months ago, but the next generation of giants is just getting started. Sheltered in their rocky nurseries, the eggs enclose pin-sized embryos. Sucking up energy from the yolk, they've grown 8 arms, red dot eyes, and their family trait, the cuttlebone. In the final month, the embryo's eyes fully develop, and still hanging upside down, they start moving around. By now, the egg's soft shell has stretched to double its size, and the bodies have outgrown the yolk ball. they start floating upright, the little giants prepare for the outside world. All their organs are now developed, and they can already change the color and shape of their skin. After about 4 months, they squirt a special acid from the tip of their tail to burn a hatching hole through the rubbery shell. Barely the size of a fingernail, the tiny giants emerge like miniature adults, with suckers, ink, and all. Nobody knows how many will survive. In a few days, they'll start hunting tiny shrimp and perfect their shape-shifting repertoire. But they've got to watch out. They're on the menu for almost anything with a fin. Sharks, big fish, seals, they all love cuttlefish. Their meaty bodies without spines or armor make cuttlefish a protein-rich meal. Camouflage is the cuttlefish's main defense. While they're invisible, they're safe. But once the cover is blown, their only chance is to disappear behind an inky cloud. Dolphins have developed a special taste for cuttlefish. But rather than gorging on the whole body, they prefer to just pick off their soft arms and heads. Leaving behind tattered bodies, they provide a free meal for many more creatures. But cuttlefish don't just end up on ocean dwellers' menus. In many countries, humans are one of cuttlefish's most voracious predators. Cuttlefish, octopus, and squid are eaten around the globe, harvested on a large scale. The total reported world catch is more than 3 million tons per year, worth more than $6 billion. Our taste for all things calamari overwhelms even their best camouflage. But is there one cuttlefish no one should ever eat? Back at Australia's Institute for Molecular Bioscience in Queensland, Mark Norman is about to find out if the colorful, flamboyant cuttlefish is truly poisonous or just a poser.
That's worth looking at. Toxicity is really rare in these sorts of animals. There's thousands of species of octopus, squid, and cuttlefish, and in all the world, there's only blue-ring octopuses, and just recently the little striped pajama squid are the only ones that are known to be poisonous, to be very deadly. And so, trying to understand the behaviour of this strange little cuttlefish, I think it's really important that we find out whether it's pretending to be something else that's dangerous or it itself is dangerous.
Toxins could be anywhere, from the skin to the inner organs. If the flamboyant's bite is toxic, its saliva will contain the poison, just as in the blue-ringed octopus. But it could also be mixed in with its ink. Mark needs to analyze all body parts. And the results?
Well, it turns out that flamboyant cuttlefish is toxic. It's as toxic as blue-ringed octopuses, and blue-ringed octopuses have killed humans from their bites. So we've got the first deadly cuttlefish in the world, and it's amazing on a couple of levels. First of all, it's actually poisonous flesh. The mussels themselves are poisonous. So this is the first time that flesh that is deadly has been reported in any of these groups of animals. And secondly, the toxin itself is not known. It's some completely different class of toxins. And toxins like those could be the key to whole new discoveries for lots of human medical conditions.
But beyond any potential medical use, the toxin is exciting to Mark because it helps explain the flamboyant cuttlefish's oversized confidence.
This is a fantastic result because it makes sense of what we're seeing in the wild, and this toxicity, this poisonousness, is probably what's underpinning the whole weird behaviour of the animal, and the fact that a group of animals that normally swim around or spend a lot of time trying to be camouflaged have become so obvious, have given up swimming, are walking everywhere. It's like a major step towards a whole new line in the evolution of these animals.
Evolution means change. So maybe in a few million years, the flamboyant will march on 8 legs right onto the beaches. Or the broad club will hypnotize its predators as well as its prey. Perhaps the Australian giants will invent even more daring strategies to outwit their rivals. Cuttlefish are amazing and perplexing creatures, and we're still trying to understand how all this talent evolved.
We are testing an animal that's very alien. I mean, it's as close, perhaps, as we're going to get to studying an animal on another planet. And is that exciting? That's very exciting.
We do not know how smart or clever a cuttlefish is because every time we go and do a serious bit of field work or a lab experiment, we continue to learn new things about their capabilities for learning or memory or hiding. So I think we have much more to learn.
I hope in my 80s and 90s I'm still wandering around underwater with a walking frame following these things around, because it'll take 100 lifetimes to get a handle on these animals.
Cuttlefish continue to dazzle with their outward displays. But exactly what goes on inside their heads will remain, for now, the real mystery.
On Nova Science Now, do you hate broccoli?
Broccoli. Remember, eat your green vegetables. All right, so activity tomorrow, and we'll probably hand those papers out tomorrow as well, just on account of a lot of you aren't going to be here on Wednesday. You'll be doing your acting class, ACT. Their acting class. Okay, so we will catch up to you next time. Beep, 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 beep. That's, I'm not very good at that. Catch up to you next time.